Now we look at the torque that makes all this happen. We have mg acting straight down, and the beam is at angle theta with respect to horizontal. You might have to twist your head a little bit. This thing was drawn from an awkward angle and not drawn all that well. The horizontal should be perpendicular to the mg, and the whole thing should be tilted over quite a bit, but we're going to try to live with it as it is. This is supposed to be horizontal, this is supposed to be vertical. So adjust your imagination. If we have a beam, and if r stands for the distance to the center of the beam, r being a typical letter to use for the moment arm when we're figuring out a torque, then what we want to do to figure out the torque here is to multiply the moment arm by the component of the weight that's perpendicular to the moment arm. Now there's another way to do it, of course, but this is the way we're going to do it in this example. So we take the weight and we find its components mg cosine theta and mg sine theta, perpendicular and parallel to the incline of this beam, and we multiply the perpendicular component mg cosine theta by the r. So we do f perpendicular times r. R in this case, if L is the beam, is going to be 1/2 L. So we end up with mg cosine theta times L over 2. The alternative way to look at this, and sometimes it's better to look at it one way and sometimes the other, is to see the beam here and the mg acting straight down, and to measure the moment arm perpendicular to the force that's exerting the torque. So we come over from the point of rotation at a perpendicular to the line of the force, and we measure the moment arm in this direction. And the moment arm will of course be r cosine theta. The trigonometry here is very straightforward. The torque then is F times r cosine theta. The F is the mg of the weight, and the r cosine theta is L over 2 cosine theta. So we get torque is mg times L over 2 cosine theta. This is of course the same thing we got here. Now let's digress for a minute. And think about all the forces that might be acting on this beam. You see, we have the weight components, mg cosine theta and mg sine theta. If we want to hold the beam in equilibrium, we could do this by exerting a force mg cosine theta in this direction, but that wouldn't quite be enough. We'd need an mg sine theta in this direction. If this is a bolt through the beam, then the bolt will exert a force of that magnitude and in that direction to counter the mg sine theta weight component in this direction, just as the mg cosine theta counters the mg cosine theta here. If this is a meter stick resting on a tabletop, then this mg sine theta force is actually a resultant of my thumb, which has to exert the force that goes in this direction, and the tabletop, which exerts the component of the force in this direction to help balance, to help support the beam. The reason the beam slips is because unless we do have a force mg sine theta in this direction, we're going to have an acceleration in the direction of this weight component. If there isn't enough friction, if my thumb isn't there, if there's enough friction, then the beam doesn't slip. But as the beam falls, we get more and more weight component in this direction. Actually, we get less weight component, but we get less and less normal force down here in response to this weight component, and we get less and less friction. So what happens is eventually the beam will slip, and that's an interesting problem to solve. Just exactly what angle will the beam slip if we know the coefficient of friction. But we're not going to get into that here. By contrast, we could balance the beam by exerting a force of 1/2 mg cosine theta out here at this end of the beam. Now we still have weight components here and here, and we're still going to need a force mg sine theta to counter this mg sine theta. But if that's all we have, if we don't have this force in the green here, it turns out, then we're not going to be in rotational equilibrium. If we calculate the torque about the bolt here, we find that the torque is, of course, 0. I'm sorry, I said if we don't have the green force, we wouldn't be in rotational equilibrium. That's not the case. Well, actually, we will be in rotational equilibrium. Let's go on. Okay. Okay, in the first place, we can see that this force will balance this because the torque about the bolt is going to be the moment arm here, which is L over 2 times the mg cosine theta, in the counterclockwise, or in the clockwise direction, which is negative L over 2 mg cosine theta. The torque of this will be in the clockwise direction. Moment arm is L times 1/2 mg cosine theta, and these clearly add up to 0. If we do the torque about this end, we see that the mg cosine theta exerts a torque of L over 2 mg cosine theta, and that's actually going to be in the negative direction. Let's make that negative. And then this force down here is going to be required to balance this torque. And we're going to be able to solve for this. And this is force of the bolt perpendicular to the beam.